All right, so now we're going to talk about catalysis of lipids, which is known as beta oxidation. Okay, so when we were talking about the lipids chapter, we talked about how the cell will store energy in forms of fats, and in particular, when you think of like fat storage, what you're really thinking of are these triacylglycerols, right? So that's the glycerol, and each triacylglycerol has three fatty acid components. Okay. Um, Really what we're talking about when we're talking about beta oxidation is the metabolism or the catalysis of those fatty acids, right? So we've broken our triacylglycerol into its fatty acid components, and we can metabolize those fatty acids in order to get energy. All right. Truthfully, the glycerol can also be converted into some energy as well, but we're not really focusing on that. We're focusing specifically on the fatty acid metabolism. And again, that's called beta oxidation. The reason why it's called beta oxidation is because our fatty acids have this sort of nomenclature scheme that we haven't talked about before, but where basically you start from the carbonyl carbon. The carbonyl carbon is your first carbon. The carbon next door is what's called the alpha carbon, and the carbon next door to that is called the beta carbon. You can keep on going down the line, the gamma carbon, et cetera, et cetera. But the reason why it's called beta oxidation is because the oxidation is going to occur here at the beta carbon. Okay, so we're going to see that this beta carbon gets converted into a carbonyl group, and then this 2-carbon chunk right here gets chopped off. Okay, and what this does, beta oxidation does, is produces acetyl-CoA. Right? And we talked about how acetyl-CoA can be put through the citric acid cycle and then finally through the electron transport chain to generate a ton of ATP. So our beta oxidation creates acetyl-CoA. It'll actually also have an output of NADH and FADH as well. Okay. So yeah, so all of this is the first thing that has to happen is what's called activation of the fatty acid, and this actually requires an input of ATP. So what we're going to say is this first step, you have to activate your fatty acid, requires an input of energy, and then every step after that gives you an output of energy. Okay. The ATP, in order to activate your fatty acid, is actually converted to AMP instead of ADP, so it loses 2 phosphates. So because of that, we say that activation requires 2 molecules of ATP. That's kind of a little bit of a fudgy way to say it because it really only requires 1 ATP, but it's converted to AMP. So in terms of how much energy is lost, it's as if you lost 2 molecules of ATP. Okay, so step 1 is going to require an input of energy. Now every step after that is going to give us an output of energy. And the ATP attaches this acyl-CoA to the end of that fatty acid. Okay, so what's going to happen is first you're going to have this oxidation step, which generates FADH. Remember, FADH is going to be used in the electron transport chain to generate energy. That creates a double bond, and then you have this oxidation step to create a carbonyl on that beta carbon. That again gives you this output of energy in the form of NADH. And then you have what is essentially going to be, so now you have this fatty acid, and you're going to break off the last step here, cleaves this right here, and gives you an acetyl-CoA. So this is acetyl-CoA. We talked about how that will go through the citric acid cycle and then through the electron transport chain, and it leaves you with your fatty acid back again. It's your activated fatty acid, but notably now we've decreased in length of 2 carbons, right? So one of the things that wasn't necessarily pointed out, but you may have noticed, is all of the fatty acids that we talked about all have an even number of carbons. Okay, 16, 18, 20, 22, etc. There's an even number of carbons for that fatty acid. And that's because beta oxidation of fatty acids will occurs to break it down in 2 carbon chunks. So each cycle of beta oxidation will result in 2 carbons being removed from that fatty acid. Okay, each step will generate 1 FADH, 1 NADH, and an acetyl-CoA is the chunk that you break off. At the end, the last step, you're left with 2 acetyl-CoAs. Okay, so in this is for a particular fatty acid that contains 10 carbons. That means that there's going to be 5 2 carbon chunks. Right? Again, each round of beta oxidation chops off 2 carbons. So that means there's going to be 4 rounds of beta oxidation, because again, that last step leaves me with 2 acetyl-CoAs. So I'm going to get 4 rounds of beta oxidation. That will lead, since each round produces an FADH, I'll have 4 FADH and 4 NADH. And I'll be left with 5 acetyl-CoAs. Right, because each round of beta oxidation produces an acetyl-CoA, and then that final round, I'm left with 2 acetyl-CoAs. So the important thing here that you're going to need to do is, based on the number of carbons in that fatty acid, you want to know how many rounds of beta oxidation occur, how many FADHs are produced, how many NADHs are produced, and how many acetyl-CoAs are produced. Okay. Importantly, each one of these is going to be converted into ATP at some point, right? So acetyl-CoA is going to be converted through the citric acid cycle and the electron transport chain to ATP. NADH, same thing. FADH, same thing. So that's where we're going with this, is how many ATPs do I actually get from the beta oxidation of a particular fatty acid? All right, so we did it before with the specific example, this 10 carbon compound. Let's do it again, but with this generic compound that has 2N carbons. Okay, so for example, if it was 18C18, that would mean that N equals 9, right? Because the total number of carbons is 2 times N. So this is this generic formula that I worked out for you guys that can kind of simplify things. So if we had a carbon that was, or a fatty acid that had 2N number of carbons, how many ATPs would require to activate? So no matter how big or small your fatty acid is, they all require 2 ATPs to activate, right? So there's going to have to be this energy input of 2 ATPs. How many rounds of oxidation are there going to be? Well, there's going to be N-1 rounds of oxidation, right? Because again, that last step actually produces 2 acetyl-CoAs. So you need 1 fewer round of oxidations than what you calculated for N. So if you had a fatty acid with 18 carbons, that would require N-1 rounds of oxidation, or 8 rounds of oxidation. At the end, you would get N acetyl-CoAs. Since there were only N-1 rounds of oxidation, you would get N-1 NADHs and N-1 FADHs at the end, right? Because each round of oxidation produces an NADH and an FADH. Okay, so this is kind of this generic formula you want to have know for a fatty acid that contains 2N carbons. Okay, so how many acetyl-CoAs are produced by the beta oxidation of palmitic acid, which is a 16 carbon? So remember, if we think about this as being C times 2N, that means that N equals 8. You're going to get then 8 acetyl-CoAs. How many rounds of oxidation are needed is going to be that N-1 or 7 rounds of oxidation. Likewise, from palmitic acid, you would get 7 NADHs and 7 FADHs, right? But 8 acetyl-CoAs. Okay, so now we're going to translate all that information into a number of ATPs that you actually get. So again, let's do the example of a 10 carbon fatty acid, capric acid. Okay, so we said that from that 10 carbon fatty acid, we'll get 5 acetyl-CoAs, right? This going through the electron transport, through the citric acid cycle and through the electron transport chain will generate 10 ATPs per acetyl-CoA. All right, so acetyl-CoA going through the citric acid cycle and then the electron transport chain, you get 10 ATPs per acetyl-CoA. Let's actually make sure that we can see how that would be. Right, so our citric acid cycle, acetyl-CoA generated 3 NADHs and 1 FADH plus 1 direct output of 1 ATP. Well, remember 3 NADHs multiplied by the 2.5 ATPs per NADH would give you 7.5 ATPs. FADH multiplied by the number of ATPs would give you 1.5, and then 1 ATP through that direct generation of the citric acid cycle, giving you a total of 10 ATPs per round of the citric acid cycle, right? So per molecule of acetyl-CoA, you get 1 round of the citric acid cycle, and each round of that citric acid cycle generates 10 ATP. Considering the electron transport chain as well. Okay, so if I had 5 acetyl-CoAs, that would give me 50 ATP just from those acetyl-CoAs, right? I think I forgot to mention, but we had to activate it, so we're going to have to subtract 2 ATP. That's the energy investment phase. Then once we get our 5 acetyl-CoAs, we'll turn that into 50 ATP. And for 4 rounds of those oxidation cycles, right, because again, it's that N-1 for the number of rounds, we would create 4 NADHs and 4 FADHs. If we multiplied that 4 NADHs by the 2.5 ATP, we would get 10 ATP after those go through the electron transport chain, and 6 ATP from our FADH after those go through the electron transport chain. So total from the beta oxidation of this capric acid, we get an output of 64 ATPs. That's a pretty good payoff. Okay, let's do it again. But again, taking this generic fatty acid that contains 2N number of carbons. So again, if I had C20, that means that N would equal 10. So make sure you're understanding how I'm getting this N number here. If you had N, well, so first of all, what's going to be the investment that you have to make in terms of activation? That's always going to be the same no matter the length of the fatty acid. You're going to have to input 2 ATPs, right? Now, if it's a CN length fatty acid, we said that that would require N rounds of beta oxidation. Those it would require N-1 rounds of beta oxidation. Those N-1 rounds would create N acetyl-CoAs. So multiplying that by the 10 we get from acetyl-CoA going through the citric acid cycle and then the electron transport chain, we get N times 10 ATPs from acetyl-CoA. Likewise, in N-1 rounds of beta oxidation, you would generate N-1 NADHs. So that would give us N-1 times 2.5 ATP. And then for N-1 FADHs that we would get from N-1 rounds of beta oxidation, we would get N-1 times 1.5 ATP. So if we stuck this all together, 10N plus N-1 times 2.5 plus N-1 times 1.5 minus 2. We can simplify, expand it all together, put all your all your variables together. We could simplify this to be n times 14 minus 6 ATPs. That's how many total we would get from a generic fatty acid with 2N carbons. Okay, so the whole purpose of me doing this simplification of this carbon, of this, take this fatty acid with 2N carbons, is to get this generic formula that we can use to figure out how many ATP is produced in a fatty acid of any length, right? All you have to do is figure out what N is and then use this formula here. Okay, so let's do this for stearic acid, which contains 18 carbons. Let's go the long way and then show that it's the same as our short way, the formula. Okay, so first of all, activation of of this stearic acid, this 18 carbon fatty acid, is going to require 2 ATPs because that's how many it always requires. Okay, if I have C18 as my fatty acid, how many acetyl-CoAs would I be able to get at the end of that? All right, so that would be 9 acetyl-CoAs. How many ATP do I get per acetyl-CoA? That's 10, so that gives me 90 ATP. How many NADHs am I going to get? That's that N minus 1, so that would be 8 times 2.5 ATP per NADH, giving me a total of 20. I would also get 8 FADH, but I only get 1.5 ATP per FADH, giving me a total of 12. So that would give me a total of 120 ATP. You could also say if C is 18, and I'm going to put it in this C equals 2N format, that means N equals 9. And you can see that if you did 14 times 9 minus 6, you would indeed get 120 as well. Okay, so being able to complete a problem like this is exactly what I want you to be able to do for beta oxidation. And I know it kind of seems like it's a lot of memorization and stuff. The better you understand the individual components, the better you're going to be at being able to solve these problems, right? If you really don't know the citric acid cycle, I mean, yes, you want to have this in your head that it's 10 ATPs per acetyl-CoA, but you can always double check it if you actually know the citric acid cycle well, right? So make sure that you're trying to learn as much about each of these metabolic processes as you can, because that'll help it all make sense together, because they really do feed into one another. Okay, the last thing we're going to talk about with regards to lipids is just this idea of ketogenesis. Okay, so if carbohydrates are not available, and by that I really mean like periods of starvation where you really just don't have any sugars around, you can't go into the citric acid cycle. So the acetyl-CoA that's created through beta oxidation, in order to get those 10 ATPs, it needs to go through the citric acid cycle. Well, the citric acid cycle requires components that are created from carbohydrates. Okay, so all those individual components aren't going to be there if you don't have any carbohydrates available. So what happens is that this acetyl-CoA molecules enter your body, the cell goes through what's called ketogenesis. Okay, your acetyl-CoA is going to start to accumulate because it can't go through the citric acid cycle. So too much acetyl-CoA is being produced. And then, so what ends up happening is your body enters into what's called ketogenesis, where those acetyl-CoA molecules are combined to form ketone bodies. This is not an ideal form of metabolism. You don't get as much energy from each acetyl-CoA. It can build up some nasty byproducts. Generally speaking, it's not great. It's your body's backup mechanism when it starts entering a period of starvation, okay? The only thing I really need you to know about this is that ketogenesis happens because there are no carbohydrates available. And again, talking about something like a period of starvation, so that no citric acid cycle happens, and instead acetyl-CoA molecules are combined to form ketone bodies. Okay, so if you have a situation where a cell has ketone bodies, it's because it's in ketogenesis and there are no carbohydrates around. That's really all I want you to know about this ketogenesis and ketone bodies. Basically just having heard it and understanding when it occurs within the cell.